Hi everyone, this is a redo of a tutorial session we had at General Physics 204 at Rutgers. You can find the high quality video files or any information at this web address here. So today we're going to talk about particles and waves. This is basically historically the story of how quantum physics begins, and right at the beginning of 20th century. Alright, at the year 1900, people couldn't quite understand the blackbody radiation. A blackbody is an object that doesn't reflect the light and it's opaque to light. So any light comes in, it just absorbs it, and also it's at equilibrium at a temperature T, and it emits light with some spectrum density. And you can think about the intensity spectrum with respect to wavelengths as a curve like this. So people couldn't quite understand why the curve goes to zero when the wavelengths becomes smaller and smaller, or when you go toward ultraviolet. Classically, if you try to calculate this curve, you will find this curve that goes up, this blue curve that goes up all the way, and sometimes it's referred to as ultraviolet catastrophe. So to be able to solve this problem, Planck suggested a solution, and the solution was that if you think about energy of a electromagnetic wave which radiates at a frequency f, what you do, you say it cannot have all the energies, but just discrete values of energies, hf, 2hf, and all the way up. So it basically can have nhf, which n is a natural number. So if you assume this and calculate the spectrum, the intensity spectrum density, what you find is this formula here which shows the curve, and it actually matches with the data points that you get from experiment quite well. So the data points can come from the sun, as I drew here. It's basically, this data points almost show qualitatively how sun emits light. But it can also come from other black bodies like universe, which is known as cosmic microwave background radiation, the photons that live in the universe. So we're not going to solve any problems on this subject, which is and just move on to the next concept. But this is the first appearance of the word quantum, which is these energy levels hf per photon. So the next, the year 1905, Einstein, along with publishing the special relativity, published this paper about photoelectric effect and explained it using the picture that Planck suggested. So Einstein believed that you can think about light as these particles, which are called photons, the same energy levels that we talked about, hf. So each photon has an energy hf, and when it hits the metal, electrons jumps out. And you can actually measure, in this apparatus, measure what's the kinetic energy of electrons jumping out of this metal. So historically, why people couldn't understand this photoelectric effect was that when they shine light on a piece of metal, they saw electrons are coming out, but it happens at a specific frequency. By accidents, they found out that it depends on frequency, but it doesn't depend on intensity, in a way that if the frequency is lower than this f star and you increase the frequency, no electron is coming out. But as long as you pass this critical frequency, electrons will start coming out, and you will see a current here in this system. So Einstein explained it as photon has energy hf, so if you pass hf star, what happens is your energy is bigger than work function, or the potential that you need to take the electron up so that it's free to move. If you write the formula, basically hf will become w0, which is the work function of a metal. It's just a number like a couple of electron volts, plus the maximum kinetic energy. The reason we're talking about the maximum here, we're not putting just the kinetic energy, is because there are other electrons which need more energy to excite and get free and move. So we're talking about the electrons just at the last energy level in a metal, that they need the minimum amount of energy, which is this W0, to go out of the metal. So basically when the photon comes in, you shake these electrons so much that it jumps out and starts moving. That's an intuitive picture. So let's talk about this experimental setup here. In the experimental setup, to be able to measure the kinetic energy max, this number here, which theory tells you that it's linear with respect to frequency, to be able to measure it, what you do, you put a battery here with EMF epsilon, which you can change, and you can tune it so that the current becomes 0. So you see some current when there's no voltage here, then you increase the voltage, and at some point the electrons which live here, they cannot make it to the next plate. That's the point where the kinetic energy max is basically equal to E times E, the E being the charge of electron, and this E is the EMF of the battery. This E is called the stopping potential, the EMF of the battery that you use to stop the electron before it reaches this plate, and it's just for the matter of experiment. The theory we have is this one formula here, which is explained at 1905. So exercise number 1, take work function to be 2 electron volts, take lambda to be 200 nanometers, which is in ultraviolet region, and find the maximum velocity of the electrons jumping out of the metal surface. So this sign here means that you can pause the video and work on this problem by yourself, and whenever you're done, you can play and continue. We'll solve it together again. Alright, I assumed you did that already. So to solve this problem, you're basically using the formula given, for the photoelectric effect, the photons with energy HF coming in. So this is basically the conservation of energy. You need W0 to take the electron out of the metal, and the rest of the energy will be the kinetic energy. And if you write the formula, Hc over lambda, HF becomes Hc over lambda because the lambda is given in the problem. So you can find the energy of a photon minus W0. It will be your kinetic energy. Your kinetic energy relativistically is this formula here, but you can use the non-relativistic formula, which is half mv squared, as you're more familiar with. And because the velocity is, if you find the velocity, you will find out that it's much smaller than the velocity of light, c. So you can easily, without any problems, you can use the non-relativistic formula. Let's get to the exercise number 2. Let's get to exercise number 2. Say we know the stopping voltage, which is 10 volts, and the work function, which is 4 electron volts. We want to find the maximum lambda, so we can have non-zero current on the circuit. So you can pause here and think about this problem. If you've done it, you can get to the solution. So here I drew the figure again, and let's go through the argument why the electrons are, this is called the stopping potential, why the electrons will stop before this plate again. So electrons, when they jump out of the metal, so there is no potential energy anymore, let's say they're in the zero potential energy here, the first total energy at this point is 0, KE1 is 0, potential energy 1 is 0, and at this point you get to the potential energy, negative E times E. So we're assuming that the stopping potential is a positive number, and this voltage for the battery must be negative E. I forgot to mention in the when explaining this concept in the beginning. So this is negative the stopping potential E. If you make this negative E, the electrons will stop before reaching this plate. So basically, when you're doing the experiment, you see that the current is non-zero, and when the voltage is positive, you make it negative and you increase it in the negative direction, and at some point it stops, and that's how you measure K, kinetic energy max. because if you add kinetic energy max to the potential energy, you should get 0 because you have the conservation of energy for this electron. So what you get is EE equals KE max, and and you have the formula for the maximum kinetic energy, which is the photon energy minus the potential energy it needs to take the electron out of the metal. So you can find the F star or lambda star. So the frequency must be bigger than F star, or the lambda must be smaller than a critical wavelengths, so that you can have a non-zero current. You can produce a non-zero current. So that was it for the exercise number 2. Before getting to the next concept, which is Compton scattering, let me remind you of these things. First, the energy for a relativistic particle, the formula for the energy and momentum are written as these, and if you have the velocity equals to, for photons, you have velocity equals to c. So you have a 0 the denominator here. To make sense of it, you can say, well, the mass of the photons are 0. So this is basically saying that if a particle moves with velocity of light, it has to have mass equals 0. So photons are massless. And if you use this energy, which is actually generally true for massive or massless particles, E squared equals P squared C squared plus M squared C to the 4th, then you put the mass equals 0. For the massless particles, you get energy is P times C. The momentum times the speed of light is the energy for a photon. But we know that the energy for a photon is the H Planck constant times F frequency. So what you get is the momentum, which is H over lambda. You can actually measure this and see that this is true for any photon also. We could have actually assumed that the momentum is this, but you can drive it using this formula we talked about. So the momentum for a photon, just remember, it's H over lambda. So you have a similar formula for momentum and energy of a photon. So let's get to the Compton effect. In a Compton effect, you shoot a photon to a particle. Let's say the particle is an electron. And by writing the momentum and energy conservation laws, you can actually solve this problem. And you can find out, for example, what the lambda prime for a photon will be in a given angle that it scatters away from the electron. So this is the initial condition, this is the initial before the collision, and this is after collision. You put a detector at the angle theta, and you measure the photon scattered off this electron. So this equation that you write, the conservation momentum, for the momentum of a photon, you will use the formula H over lambda. And for the momentum of electron, you can just simply use mv, or the relativistic formula if this velocity is going to be too large. But for typical velocities that happens in these kind of experiments, you can use non-relativistic formula because the velocities are much smaller than c. So experimentally, this Compton was trying to explain this, and experimentally he saw some formula like this, that lambda prime minus lambda was some number that we'll see what the theoretical number is, times 1 minus cosine theta. So this is experiment. This is from experimental data, and Compton was in 1923 accepting the photon description of an electromagnetic wave, believing in that this is true, that photons have h over lambda momentum, or the energy h times the frequency, Planck's constant times frequency. He was trying to explain this, so he wrote these two equations, the conservation of momentum and energy. He actually proved that this is true, and this factor here is h, the Planck constant, over the mass of the electron times velocity of light, h over mc. So h over mc is called Compton's wavelengths. This is Compton wavelengths. And that's it for the Compton effect. Let's get to the exercises, and we will learn how to use, how to write the conservation of momentum and energy, and also how to use this formula. Alright, exercise number 3. There's actually a reference to your textbook here. This is the same problem. So let's say you know theta is pi, it's 180 degrees, and the velocity electron after this collision is given. Find lambda of the photon coming in. So we can pause here and think about the problem. If you have done so, let's get to the solution. So if you write the formula that it's given, it's a simple formula. What you get is lambda prime minus lambda is h over mc, 1 minus cosine theta. Cosine theta is -1, so you get a 2 factor of 2 here. So you get 2h over mc. But this equation has two unknowns, lambda prime and lambda. So you have to write the conservation of momentum or energy, at least one of them, with this formula, or just solve conservation of energy and momentum together. The reason for this is that this equation doesn't capture all the information about conservation of momentum and energy. So sometimes this is not enough to solve a problem. So here, if you write the conservation of momentum, so this is for the P, momentum, and this is written for energy here. For the momentum for energy, momentum of a photon is h over lambda to begin with, and the electron was sitting there, it was at rest. And finally, your photon is moving toward left, so because this is a vector formula you write for the momentum, just remember that the momentum of the photon will be negative h over lambda prime. Because if you call this x direction, this is negative x hat. And in the y direction, your momentum doesn't give you any formula because before and after the collision, there's no momentum in y direction, so 0 equals 0. But in the x direction, you have this formula. Again, for the electron, because the velocity is fairly low, although it's 3 sig fix, so if you want to get all the digits right, you got to use the relativistic formula. But if you don't care and you just want an estimate, you can use the classical formula, which is mv, for the momentum of the electron after the collision. And for the energy, you can write the energy. You can use the kinetic energy of the electron here, or if you're using the energy of electron here, you should remember to include mc squared as the rest mass of the electron to begin with, on the left hand side too. So this is the energy conservation I wrote. c over lambda is the frequency of the photon before the collision and after the collision. This is the energy for the electron. Again, for the kinetic energy of the electron, you can use half mv squared as an approximation, a non-relativistic approximation. Now if you look at these formulas P and E, you see that you can solve them fairly easily. There's a h over lambda. You want to find lambda, and there's a negative h over lambda prime and a positive hc over lambda prime. So if you multiply this formula by c and just add these two formula for the momentum and energy, you can easily solve and find lambda in terms of velocity, mass, and h. I'm not going to do it here. It's just homework for you if you want to try. By homework, I mean an exercise for you if you want to try. Okay, let's get to the next exercise. Okay, this is exercise number 4, or reference to the textbook 2921. We want to find the maximum change in wavelengths of a photon, which means lambda prime minus lambda, scattering by a nitrogen molecule, N2. So this time it doesn't scatter off an electron, but it scatters off a nitrogen molecule, which is N2. So again, you can pause here, pause the video, and think about this problem. When you're done, you can continue. Alright, let's get to the solution. So this is the same formula. You have the formula for delta lambda, h over mc 1 minus cosine theta. To find the maximum amount of this delta lambda, you would see it in an angle that you get factor 2 here, right? The cosine theta, if the cosine theta is 1, you get 0. But if the cosine theta is -1, which is in angle 180 degrees, like the previous problem, the previous exercise we solved, you get factor of 2 here. 1 minus cosine pi is 2. So this is the maximum change in the wavelengths that you can have for a photon. Now you need to figure out what is this mass here in the formula, 2h over mc, but you don't know what the mass is. To find the mass for a nitrogen molecule, of course you know that you can use the atomic mass, the m, divided by the Avogadro number, it will give you a mass for a nitrogen molecule. But if, the atomic mass, the number for nitrogen is 14, so you gotta multiply it to 2, it's N2, it's a molecule. So divided by Avogadro number, that gives you the mass, and you put the mass in the formula and you find the maximum change in wavelengths of the photon. The next concept we're gonna talk about is de Broglie wavelengths. So de Broglie thought about photons having this formula between momentum, having this relation between the momentum and wavelengths. So the photons have this wavelengths, the wave property here, which explains how much momentum photon has. De Broglie took this formula and wrote it in this form, that lambda equals h over p, and said maybe this is true for anything we call particles classically. So classically we think about electron as a particle. Let's now say electron, you can assign a wavelength, which is called de Broglie wavelengths, to a particle, let's say electron, which is h, the Planck constant, divided by the momentum of that particle, p. You can actually experiment if this is true. What you can do is to send electrons one by one to in the double slit experiment and measure the intensity of electrons coming out, landing on the screen. So what you see is do you see the pattern? If the electrons classically behave and just go through one hole at a time, through this one or either this one or the other one, which you would see adding these two patterns together, or do you see an interference phenomenon, which is something that happens for waves? Well, they did the experiment and they saw, yes, you see the interference pattern, and this means that electrons are actually waves. They see both the slits at the same time, which is kind of was puzzling at the time. So what they see is actually the electrons landing on these maximum with high probabilities, and with zero probabilities there's no electrons at these minimums. So any problem we solve here on the interference or diffraction or anything else about the waves we did in a previous session, you can actually do it for particles like electron just by using the lambda, which you find using the de Broglie wavelengths. In these formulas you have, for example, d sine theta equals m lambda, this lambda coming from the de Broglie wavelengths. So let's get to the exercises. Alright, exercise number 5. We want to find lambda E for electrons, which are accelerated by a potential voltage 418 volts. So you can pause the video here and think about this problem. Try to find the wavelengths, the de Broglie wavelengths, for an electron accelerated by this voltage. Now let's get to the solution. Let's scroll, it's going to appear. Alright. So for an electron, we solved this problem before, that initially you have kinetic energy 0, the potential energy 0. You can call the voltage of the other plate delta V. If you're calling this voltage 0, you can call this voltage delta V. You can add any constant to these, like 10 volts delta V plus 10 volts. It doesn't matter. So what happens is your electron here has 0 voltage. Here it has delta V voltage, but the charge of the electron is negative E. Remember that there's a negative sign. And if you add the initial energy, it's 0. So if you add the final energy, you should get 0. Ke final plus negative E delta V should be 0. So you get that final kinetic energy is just E delta V. And you know that classically, you can write kinetic energy as P squared over 2m. So the lambda for the electron, it's going to be H over square root of 2 times the mass of the electron times the charge E times the delta V. That's the de Broglie wavelengths of the electron accelerated by this potential. Let's get to the next exercise. Okay, exercise number 6. Again, there is a reference to your textbook, problem 29.36. So assume a particle that has the same kinetic energy as a photon. So there's a photon and there's a particle. The photon has the same energy as the kinetic energy of that particle. And also we know that the velocity of the particle is 1/20th of the velocity of light. So the particle moves 1/20th of the speed of this photon. We want to find lambda of photon over lambda of the particle. These are typical values which you have in most of the experiments, 1/20th, and the kinetic energy are almost equal to the energy of the photon. So find the lambda of photon divided by lambda of the particle, and by lambda of the particle, of course, we mean de Broglie wavelengths, h over p. You can pause this here, pause the video here and think about it. Let's get to the solution. Okay. So you know that the energy, the kinetic energy of the particle is equal to the energy of the photon. The kinetic energy of the particle is half mv squared. Again, we're using non-relativistic formula because the velocities are pretty low. It's 1/20th of the velocity of light. So by a good confidence, you can just use the classical formula. And what you get is you can write the mass of electron in terms of other values, because the mass, not the electron, mass of the particle in terms of other values, because the mass is not given, so let's find the mass. The mass becomes 2hc over v squared lambda of photon. And what you get from here is you can find, using the mass, you can find the p, the momentum, and using the momentum you can find the lambda of the particle, the de Broglie wavelengths, h over p, h over mv, which becomes v over 2c lambda photon. So the ratio between the photon and particle wavelengths is 40, 2c over v, which is 40. You know that c over v is 20, so 2 times 20 is 40. These are actually the typical values. You see that for a photon you have much larger lambda than a particle. So if you want to use photons to see something, you will have the visible, let's say you're using visible light to see something, your lambda is about 100 to 1000 nanometers, so it's about 1 micrometer. So you cannot see structures that are smaller than 1 micrometer. That's why an optical microscope, there's a limit for it. If you're using your eye to see stuff, there's a limit for it, which is about 1 micrometer. Any structure smaller than that you cannot see. But using electrons, we saw that the lambda for a typical electron with these velocities is about 1 nanometer to 10 nanometers. That's why an electron microscope can actually see stuff much finer. Like you can see with a precision 10 nanometers the structures that are that small, or you can take really high resolution photos using the electron microscope from insects or anything else. So let's get to the next concept. Alright, the next and last concept that we're going to talk about is Heisenberg uncertainty principle. This is mathematically the first time that the I, square root of -1, is intrinsically needed to write down the formalism of quantum physics. It's just a side note. So to understand this Heisenberg uncertainty principle, we use the single slit experiment. So let's say the particles are coming in with the momentum in x direction, in y direction the momentums are almost 0, and we want to find out where in the y-axis these particles sit. Okay, so what you do, you make the width of this slit narrower and narrower, and it actually shows the uncertainty in the measurement of y, where in the y-axis it sits. So the delta y is proportional, it's almost w, right? The w is your uncertainty in measuring the y. But what happens when you make this slit narrower and narrower? What happens is the particles are going to end up in a wide part of the screen. If you take this wider w to be like this, the probability that you find particle on this screen looks like this, so most probably you will be in this region, which is your uncertainty, kind of showing your uncertainty. You have to measure where in the screen you end up. It's going to increase because if you make it narrower, if you learn from the diffraction theory, you remember the sine theta is lambda over w, or the formula we had was w sine theta is lambda, right? Is m lambda, and the m, this is for dark points of the diffraction for a single slit. So sine theta is lambda over w, so when you make the w smaller, the particle is going to end up in a much bigger part of the screen. Okay, so, and this depends where the particle sits on this screen, depends on the py, the y component of your momentum after passing through this passing through this slit. So this shows that by making the delta y more precise and making lambda over w bigger and bigger, you're messing up with measurement of py. So you're making py, the momentum in the y direction, to be anything in this range, in this angular range. So if you write delta py, it's going to be p sine theta, right? The momentum times sine theta shows how much delta py you have. By using h over lambda for the p, you find that delta py is h over w. So the Heisenberg uncertainty principle is, if you multiply delta y to delta py, you never can get below this value, h over 4 pi. If you measure delta y with really high accuracy, necessarily delta py will be messed up, and you can't measure it with high accuracy. So if the accuracy of if the uncertainty in delta y goes to 0, this goes to infinity. Delta py goes to infinity. So if you make this slit narrower and narrower, the particle is going to end up in whole this screen, and you would never know what is py. And if you do the calculation in the single slit that we did, this is just the approximate calculation, you will get h. But the correct formula, if you do standard deviations and go meticulously over calculations, you'll find h over 4 pi, the 4 pi factors here. So this is the formula, and the y and py is sometimes called conjugate variables. You can actually use time and energy instead of y and py, and this is actually true too. If you measure the time when something happens, an event happens, with a really high accuracy, and make it more precise, then measuring the energy of a particle, let's say, pops into existence, measuring the energy necessarily will be a really low certainty measurement. Okay, it's a really high uncertainty in the measurement. And the opposite is true. If you measure the energy really accurately, you wouldn't know when it happened. So delta t would be high. So let's solve one exercise on this uncertainty principle. Alright, exercise number 7 from your textbook, there's a reference 29.42. So there's a particle created in an experiment, decays after 7.4 times 10 to the negative 20 seconds to other particles. This is typical of most of the particles. They just decay to other particles. They're not stable. There are only few stable particles around. And we find these particles in accelerators. So find the minimum uncertainty. We want to find the minimum uncertainty in measuring the mass of this particle, how massive this particle is. And you can use the equivalence between mass and energy here. So you can pause the video here, think about it. So let's get to the solution. Okay. So the time that the particle existed, you can think about it as delta t in the Heisenberg uncertainty principle. That's the time that the particle exists, which means that in the time axis, you know that the particle exists in any time from like t1 to t2. The difference is this much, 7.4 times 10 to the negative 20 seconds. And using the Heisenberg uncertainty principle, you can find delta E, because you know delta E times delta t is h over 4 pi. So delta E must be bigger or equal to h over 4 pi delta t. This gives you a minimum mass for the particle, minimum uncertainty, maximum uncertainty of the particle, which is 10 to the power 1 kilo electron volts. You can find it in terms of joules too, and the mass will be 1 over c squared times this number here. And this number is actually 1,000th of the mass of electron, which is pretty accurate if the mass is higher than mass of the electron. So, but this is the limit of your experiment. Even though you make your experiment accurate, more and more accurate, this limit is going to stop you to finding out what the mass value is. So that's it for the exercise number 7, and we're done with the session on particles and waves.